Let's look at factoring the difference of perfect squares. So when we have a problem such as x squared minus 16, we can think of that as a trinomial where we have x squared plus 0x minus 16. So here, normally we would treat this as that special case trinomial where we find two numbers that add to give us 0, multiply to give us negative 16. We find those numbers to be negative 4 and 4. Whenever we have that linear term, that middle term, to have a coefficient of 0, we know that the only two numbers that add to give us 0 are additive inverses, meaning the same number, opposite signs. But if we think about it, if we multiply a number by itself, that's the same thing as squaring. That makes 16 one of our perfect squares. So here we have the difference of two perfect squares because our coefficient here is 1. That's also a perfect square. And any variable with an even exponent is a perfect square. Because to take the square root of a variable with an even exponent, that's the same thing as raising it to the power of 1/2. And we know when we have a power raised to a power, we multiply, meaning here we have the power of 1/2, we're dividing it by 2. That's why we can take the square root of a variable with some even power because we're just dividing it by 2. So the shortcut here, our special case, the difference of two perfect squares, is if we realize that we're subtracting one perfect square and another perfect square, that our factors will take the square root of that first term, the square root of that second term, and then we make one factor positive, the other one negative. And we know the order doesn't matter. So let's try an example. If we have x to the 4th minus 25, we see, okay, there are two terms here. We're subtracting them, and both terms are perfect squares. So to factor, we know we're going to have two factors. Take the square root of our first term, so we divide 4 by 2 to give us x squared. Take the square root of our second term, the square root of 25 is 5. And we make one factor positive, the other one negative. Let's try one more example. What about x to the 10th minus 49? Because we have the difference of two perfect squares, we divide 10 by 2 to give us x to the 5th. And the square root of 49 is 7. We make one factor positive, the other factor negative. All right, what if we have a coefficient in front of our x squared term, our x to the 4th term? That coefficient has to be a perfect square as well for this to work. So here, this is just 4x squared minus 9. Before we factor that as a special case, I want to show you that we could still split our middle term here. Using our knowledge of factoring trinomials when a is not equal to 1. So splitting the middle and factoring by grouping always works, but this as a special case can go a lot faster if we notice that we're subtracting two perfect squares. As you can already tell, the square root of 4x squared is 2x. The square root of 9 is 3. And we make one factor the sum and the other factor the difference. So let's try an example. Here we have the difference of two perfect squares. If you're ever unsure if a number is a perfect square or not, you can take the square root of it, and if it gives you an integer, it is a perfect square. If you see a decimal, some irrational number, that's not a perfect square. Right here, the square root of 49 is 7. Square root of x squared is just x to the power of 1. The square root of 64 is 8. We make one factor positive, the other factor negative. All right, let's do one more. So here we have the difference of two perfect squares. So we're going to have one factor be a sum, the other factor be a difference of the square roots. The square root of 100 is 10. The square root of x to the 8th is x to the 4th. The square root of 169 is 13. And we make one factor the sum of those square roots, the other factor the difference of those square roots. So that's how factoring the difference of squares is one of our special cases where we're using not only our knowledge of perfect squares, but our knowledge of taking the square root of both those perfect squares and variables with even exponents.